This week.
Sorry, guys. Technical difficulties. Sorry, guys. Technical difficulties. I have no idea how to turn on that. Oh my God. Okay, here we go. There's no buttons on the Mac down there. How am I supposed to know if it's on? Such a boomer. I feel like such a boomer right now. Sorry, guys. It's turning on, I think, hopefully. All right, we're in business. It's because the heat wave cooked all the electricity here. To just bring my laptop. Okay, I think that's working. Let me go ahead and share screen. Okay. We are live now. Good. Okay, we'll go with that. How's everyone doing today?
It's too hot.
It's too hot. I agree. It fried all the circuits here in the classroom, apparently. Can everyone on Zoom hear me okay?
Yeah, I can hear you.
I'm going to assume yes. Okay, good. All right, so we're back. It's week 3. We have a full week of class today. Today we're talking about muscles. Sorry I couldn't get the learning objectives up today. I was kind of fighting with the Mac system here. Maybe I should just bring my own PC from now on. Okay, so announcements, homework 1's due this week. I think probably the last of what you're gonna need for the homework is what we're gonna talk about today. So you will, you'll be able to have that for your knowledge, okay? I'm hoping we can finish all these tissue biomechanics stuff this week. So we're going to go over muscles today. Wednesday, we're going to go over joints. And then next week, we'll start to do some calculations. And so we're gonna do next week. The plan is to do just a brief review of mechanics. That's just like forces, free body diagrams, stress, things like that. And then we'll start going over, the biomechanics of different parts of the body. All right. So, this class does, start a little bit slow. There's just kind of a lot of prerequisite information that we kind of have to go over. So, it's a lot of just conceptual stuff. So, but, I think after this week, we should start to be able to do some stuff. Okay. Other announcements today. I hopefully everyone got my email. Office hours today. I do have to cancel them. Just because I've been volunteered, or I guess voluntold to organize our welcome social today. So we're gonna have pizza. Basically right after the class is over, I need to run to my car, drive to Little Caesars, pick up the pizza, come back. So there will be pizza. Hopefully I got enough for everybody. And yeah, hopefully to see you guys there. So it'll be 6 o'clock at the engineering building in E101. So if you walk into the engineering building, it's just the conference room on the left. Okay.
You have one box for a person?
Depends how many people show up.
That is true.
If 10 people show up, yes, it'll be 1 box per person. But okay, good. We can always order more pizza. So if a lot of people come, I can order more pizza. All right, any questions I can answer before we get started for today? Okay, all right, so let's get started. So the topic for today is muscle biomechanics. Okay. All right, so last time we met, last Wednesday, we talked about bones, right? And we talked about bones providing the structure, the rigidity, the strength, for the human body, right? Muscles attach on top of the bones. And honestly, the muscles are probably what we're going to talk about the most in this class. And, and this is not the only time we're going to talk about muscle biomechanics. You can think of today as kind of like an introduction, just kind of with the essential knowledge that you kind of need to know just for the first part of the class. But then once we get to more advanced stuff, mostly human motion stuff in the second half, we'll revisit muscles there. Okay. So today's just kind of the introduction. So what are muscles used for? So, when we're talking muscles in this class, 99.9% of the time, we're talking about skeletal muscles. Okay. And so if you remember from the first week of class, there are 3 types of muscles that are characterizing your body. There's cardiac muscles, which are the muscles that kind of in your heart. There's smooth muscles, which are the muscles that line your internal organs and blood vessels. And then there's skeletal muscles. And skeletal muscles get their name because they attach directly to your skeleton or your bones. Okay? And their main role is to give your body a way to create motion. Okay. Okay. Muscles are kind of the way that we as humans can do a lot of the things that kind of make us happy. Get around, move around, run around, wave your hands in the air like a crazy person, right? All of these are responsible for from muscles. Okay. And the reason they do this is because muscles are the only type of tissue in your body that are able to generate their own force. Okay? And that's going to be essential, right? A lot of the cells in your body, they're able to generate, kind of small amounts of force just to kind of move nutrients from point A to point B. But when you're talking about actual force that you can, actually kind of notice on a macro scale, muscles are really the only ones that are able to do that. Okay. Okay. So let's start by talking about kind of, the same way that we started our discussion on bones. Let's talk about some of the behavioral properties of muscles. Okay. So first thing I want to mention is that in contrast to bones, muscles and tendons for that matter too, actually, most of the tissue in your body, but muscles that in particular can be characterized as soft tissue. Okay? And just kind of informally, if you kind of touch your muscles, they feel softer than your bones, right? But it kind of goes beyond that too. So by soft tissue, what we mean is that they can kind of change its shape, they can change its length to a much bigger degree than your bones. And that ability to kind of dramatically alter its length and dramatically alter its shape is really essential for it to perform the duties that it needs to. Okay. Okay. And so, that's kind of the broad kind of characterization. So let's go over kind of what I consider the four kind of essential properties or essential behavioral properties of muscles. Two of these are what I'm going to call the passive properties of muscles, and two of them are going to be the active properties. Okay, and I'll go over kind of what that means in a second. Okay. So the first one kind of goes along with kind of its characterization as a soft tissue. The first property is called extensibility. So just like the name implies, extensibility is the ability to be stretched or to be increased in length. Okay? And that kind of goes along with its characterization as a soft tissue. Okay? Okay. The second property is called elasticity. Okay? And this one, actually should be very familiar to those of us who work in kind of mechanical engineering and are familiar with how properties or how materials behave. Okay. So elasticity, just like any elastic solid, like a metal or rubber or so on, is the ability to return to its normal length after being stretched or compressed. Okay. So any material that we characterize as an elastic solid has this property here. Okay. Most engineering materials that you guys are used to working with are considered elastic, right? So these things are not necessarily unique to kind of muscle tissue. So I like to call these two properties the passive properties. Okay? Because the muscles themselves don't actually have to exert any energy or any force in order to obtain these properties, right? So just by being a passive material, an elastic material, it's able to kind of do both of these things. Okay? I want to spend a bit more time on elasticity though, just to kind of elaborate on this further. Okay. So just by nature of being an elastic solid, and so just by nature of having the ability to return to its resting length, without any kind of external influence, means that internal forces develop naturally within the material or within the muscle, when it's stretched or compressed. Okay. We can feel this kind of every day in materials that we kind of stretch ourselves, right? And so if you think of like a rubber band, right? And so if you think of rubber band, right? If you pull on it, right? So you take your two hands, you kind of pull on the rubber band like this, right? It's going to get stretched. Right? It might look something like this. And then as you pull it further and further apart, it gets harder to pull because internally we have forces that are trying to return the rubber band to its resting size or its resting length. Okay? And so we call these forces we often call them the internal forces or elastic forces. Okay? And believe it or not, your body actually makes use of this fact right here, even kind of without you knowing about it, right? And so if you think about, try to kind of imagine yourself doing kind of a very large motion or very kind of big task, right? Like imagine yourself, imagine someone dared you to jump as high as you can, right? And so what's kind of the natural thing that you do whenever you want to do something like jump really high? You crouch down, right? Okay. Let's assume that there's no running start or anything like that. It's just a standing jump, right? And so by crouching down, right? So by crouching down, you kind of get your body into a position like this, right? the main muscles that are used in you jumping, there's a lot of muscles involved in a jumping procedure, right? But two of the main ones that are used are your quadriceps, which are the muscles that are kind of on the front of your thigh right here. The other muscles that are heavily involved are your calf muscles or your gastrocnemius in the back. Okay. And so if you look at this motion right here, you can see that if you look at the hip joint, right? This hip joint is in flexion, right? And so you're kind of bringing your knees as close to your body as possible, right? And so by kind of bending your knee like this, right? Because the quadriceps kind of attaches over the knee like that. What you're doing is you're stretching out the quadriceps as much as possible. Okay? Same thing with the calf muscles. And so by kind of putting, you're kind of naturally pointing your toes up in dorsiflexion. What you're doing is you're stretching your calf muscles out as much as possible. Okay? And so by giving giving your muscle this extra stretch, you're kind of giving yourself kind of a boost in jumping power, right? Because when you actually go to jump, not only are you going to have the active forces of your muscles actually contracting, you have the passive forces from the stretch helping you out as well. You can try to think of any kind of big motion. So like if you think of a pitcher throwing a baseball, right? And so if you ever watch baseball pitchers, they go through a very large kind of motion, kind of big windup before they throw the ball because they want to throw it as far as possible. They kind of have to wind up and kind of stretch as many muscles as they can before they finally kind of unleash like that. Okay. So these passive properties of the muscles are actually really important, and they play a really big role in terms of how we use our muscles to perform kind of everyday tasks. Okay. All right, any questions on that? Okay. All right, so those are the two passive properties of muscles, and so these passive properties, like I said, these should be pretty familiar to us as engineers because most material is going to behave the same way. But of course, our muscles are not just passive structures; they are able to actively generate force. Okay? And so these last two properties that I'm going to discuss here are the active properties of muscles. Okay, the first one, or I guess the third property overall, is called irritability. Okay, and so irritability responds to a muscle's ability to respond to stimulus. And so what do I mean by that? And so if you innervate a muscle, and so if you send an electric signal to it, sometimes if you hit the muscle in a weird way, the muscle will respond. Okay. Okay. And in fact, this is the main way that your nervous system or your body controls your muscles is through electrical signals that come down from your brain. Okay. But also, I think everyone's kind of done the knee-jerk test where they kind of sit on a table when someone hits your knee in the right spot and it causes you to kick out, right? That's also kind of the irritability reaction from your muscles as well. Okay. So your muscles need to be able to do this in order for us to control. Okay. So it has to be able to respond to stimulus. Okay. And then number four, the fourth ability is the fourth property of muscles is the ability to develop tension. Okay. So this one's pretty self-explanatory. So this is the ability for muscles to generate force and contract. And it's important to kind of distinguish that these are kind of separate from the passive elastic forces. And in fact, kind of the mechanism that generates this tension is different, which we'll talk about right after this. All right, any questions on this so far? Okay. All right, so those are the four main properties of muscles, and in kind of its own way, they all kind of relate to a muscle's ability to generate force. Okay. So let's talk about that. So let's talk about property four, and let's talk very briefly of how this happens kind of on the cellular level. So let's talk about the structural organization of a muscle fiber. Okay. So you've probably heard the term muscle fiber before. So muscle fiber kind of refers to a single muscle cell. Muscle fibers are kind of a unique cell in the body in that they're kind of massive compared to many of the other cells in your body, right? Muscle fibers are kind of so big and so long that they're actually one of the few cells that are kind of observable from the naked eye. Okay. And so if you count the number of muscles in your body, well, I shouldn't say that one muscle is kind of comprised of multiple muscle fibers. Oftentimes, hundreds or thousands of muscle fibers kind of packed together in parallel. And so if you look at the cross section of a muscle, right? That's my very poor drawing of a muscle, right? There's no muscle that looks like a cylinder. But what you're going to see is a lot of little muscle fibers kind of all kind of packed together. It's almost kind of like a steel cable, right? So each little circle like this, those are all each muscle fibers. Right? And so what we call a muscle in the body is we often describe a muscle as a particular group of muscle fibers that produce a unique motion or unique kind of role. it definitely gets a little bit tricky because, you know, there are muscle groups in your body, which are multiple muscles kind of all kind of producing similar motion. But each individual muscle, you know, they may have a unique attachment point, they may have a unique direction where, you know, they all kind of work together to produce a motion. Okay. But generally speaking, you know, what we call a muscle or you know, muscles in your body that have a unique name are often the ones that produce a unique motion in some kind. Okay. But oftentimes, you know, those muscles are working together with other muscles to produce kind of complex motion. Okay. So if you count the number of muscles in your body that each produce a unique motion, there are about 434 muscles in the human body. Okay. It's important to note that, you know, we don't have voluntary control over all of these. A lot of these govern kind of involuntary motion, like swallowing or breathing or things like that. Okay. Okay. And so if you're talking strictly just on the voluntary skeletal muscles that govern our limb movement, there are about 150 of those, or in other words, 75 muscle pairs. Okay. Oftentimes you will see the 75 number reported because, you know, you have kind of identical muscles on the left and right sides of your body, right? So yes, you do have two unique bicep muscles, but, you know, one's on your left arm, one's on your right arm. So that's why we often say there are 75 muscle pairs. Okay, one for the left, one for the right. Okay. So how do these muscles actually generate force? And so to kind of answer that question, we have to go down to the cellular level. Okay. And so if you look inside a muscle fiber, the way that a muscle generates force is through the interaction of its protein filaments. And there are two filaments that do this. And so there are the myosin filaments and the actin filaments. So the myosin filaments. So filaments are often called the thick filaments. I was going to write a definition here about what they actually do. I think it's kind of easier to just kind of show you a picture, but it's good to know kind of what they are. Okay. Okay. So on the cellular level, you know, these two filaments kind of look like the following. And so first, I'm going to draw the actin filaments. And so the actin filaments kind of form a sheet around your muscle like this. Okay. So these are the actin. And then in the middle, are the myosin filaments. And so the myosin filaments kind of look something like this. Visibly, they are kind of thicker if you kind of view them under a microscope. Okay. And myosin have all these little kind of heads. Okay. We can draw it a bit better. I always draw these in the wrong direction. So the myosin filaments have all these kind of little tendrils that kind of attach to the actin. I tried for a slightly different drawing this time so you can see the head, but the myosin heads, but it kind of looks like a bug now. I'm kind of creeped out a little bit. Okay, so what happens? And so to generate force, what happens is that the myosin filaments literally kind of pull together, right? And so what's going to happen is that all of these myosin heads are going to rotate this way. And what that does is it brings the actin filaments kind of closer together, right? And so after one power stroke, right? So one kind of motion of the heads to kind of pull together. What you would see kind of on the cellular level is that the actin filaments are kind of brought closer together like this. Okay? Okay. And then those myosin kind of tendrils kind of all kind of straightened out. Okay? Okay. And then through this action, kind of two things have happened. On the one hand, force was generated, so it required force to kind of forcefully kind of pull the actin closer together. Okay. So that's the first thing. The other thing that happens is that the entire muscle kind of naturally gets shortened or contracts. Because even though this may not seem like it shortened a lot, right? So the total amount of distance that it closed here, I think there's kind of an exact number for it, but it's somewhere on the order of about 3 microns. Okay. And so 3 microns is not something that you would normally be able to observe. But remember, this is one kind of, we call this a one single kind of power unit within a muscle, and there's kind of millions of these kind of lined up end to end. So while each individual unit of kind of myosin and actin film may only kind of move a few microns, if you do this multiplied by 1,000,000, then that's kind of what generates your muscle shortening. And each one of these individual units is known as a sarcomere. Okay. All right, any questions on this? Yeah.
So, I don't know if this counts as being graphic, but like when you have a steak or something, you're always told to cut against the grain versus with the grain. Is that because of muscle fibers? Is that was, oh, okay.
Exactly. Yeah. So those fibers that you observe in kind of steaks or meat or stuff like that, they're exactly like this. And certain cuts, depending on how, and you hear this if you cook a lot too. Certain cuts are more fatty. They have less fiber than other ones because those muscles are usually involved in more movement. And so so the muscles that are more used in kind of movement, they're active a lot more. They have kind of tougher fibers because they have kind of stronger kind of protein filaments. Whereas muscles that are close to the ribs that as an example, they're not really used all that much, and so those are the more tender cuts that don't have a lot of fibers to them. So, yeah. Any other questions on this? Okay. All right, so let's go over another definition. So there is another way that we can break down muscles. There's lots of different kind of characterizations and kind of groups of muscles that we can talk about. But let's talk a bit more about kind of a muscle's ability to respond to nerves. Okay, and so let's define something called a motor unit. So a motor unit is a group of muscle fibers that are usually contract together. And if you're kind of trying to keep track of kind of how this kind of fits into our other definitions, one single muscle can often be comprised of multiple motor units. Okay. The way that I like to think about it is that a motor unit, it kind of are, they're kind of, I would say, irritated or innervated together. That was kind of a terrible way to put it. They usually are attached to the same nerve. Okay. Because remember, the way your body controls its muscles, that it sends kind of these small electrical signals from your brain to your muscles, right? But there's often multiple pathways or multiple nerve signals that can come from the brain to your muscles, right? So any given muscle, right? So let's say that we have kind of a big muscle like this, right? It may have several connections to your brain or the nervous system like so. Okay? So each of these little lines that I'm drawing here is kind of one kind of nerve. And each nerve kind of hits kind of a group of muscle fibers kind of in its immediate vicinity, maybe like so. So what happens that when your brain sends a signal, right? Usually the way it works is that your brain will send a signal to contract, right? Right. So let's say that your brain only sends a signal down this nerve, then this muscle or this motor unit will contract. Right. So that's kind of what we describe as a motor unit, is that the group of muscles that kind of respond together, or they almost always contract together. Okay? Now there's some overlap, right? So there are some muscle fibers that may be innervated by multiple nerves at the same time, but usually not more than kind of two or three, okay? And this is really interesting to think about because, depending on where the muscle is in your body and the types of motion that it can produce, one single motor unit may contain anywhere up to, as little as maybe 10 muscle fibers. So that might be for motions that are very kind of fine, very delicate, you need a lot of precision, right? So a lot of the muscles that are in your hands and your arms that are, kind of produce most of the complex motion in our body. And some motor units can contain up to 2,000 muscle fibers. So a lot of the muscles in your lower body that can't really it's unless you work for like Cirque du Soleil or something like that, for the most part we can't really control our legs to as high a degree of as our hands or our arms, right? So a lot of the muscles in your legs may have very large motor units or thousands of muscle fibers connected to a single nerve. Okay. And this kind of partially explains, why certain people are kind of better or more delicate at certain tasks because, maybe they have motor units that kind of allow for finer control of motion. Surgeons belong to that category. Surgeons have to be very, very steady with their hands. So, most surgeons, I wouldn't be surprised, would have, tons of motor units, each with, maybe only a few muscle fibers attached. Okay. Any questions on this? Yeah.
The amount of muscle fibers differ from like in one muscle might differ from person to person.
Oh yeah. Oh yeah. There's a lot of variability in that. And so and even just the amount of nerves that you have going to your muscles too. So one person may have lots of different nerves that can allow for very complex fine control motions where another person may not have as many. So yeah, there's something that varies a lot person to person as well. Okay. Another distinction, last one for now, that we'll have for muscles is probably you've heard these terms before. Is we can characterize muscle by how quickly they achieve maximum tension. Okay. So there's two categories of muscles that we use to describe this. So first being fast twitch muscles. And the other is, of course, slow twitch. Okay. And if you look at what's happening kind of at the cellular level, what kind of differentiates fast twitch muscles and slow twitch muscles is how quickly the sarcomere can kind of shorten its length. Okay. And so scientists have done a study. So this was a study of Fitz from 1991, and I believe it's been confirmed for the most part by other studies, is that fast twitch muscles in humans have a shortening speed of 4.85 sarcomere lengths per second. whereas slow twitch muscles have a shortening length of 0.86 sarcomere lengths per second. You can see there's a pretty big difference, right? And so generally fast twitch muscles, those are, what we kind of associate with kind of explosive, kind of fast movements, whereas slow twitch muscles are more for kind of steady endurance type muscles. So kind of the downside to fast twitch muscles is that they kind of tire out a lot more quickly. So slow twitch muscles are better for sustained tension just because they have better endurance. They don't tire out or use energy as quickly. So, I get asked this all the time whenever I bring up fast twitch and slow twitch muscles of, which muscles in your body are characterized as fast twitch and slow twitch. Turns out it's a little bit more complicated than that, this characterization of fast twitch and slow twitch, these are kind of characterizations on the muscle fibers themselves. But of course, a muscle that we kind of think of is made up of, thousands or hundreds of thousands of muscle fibers in parallel, okay? So when you're talking about fast twitch and slow twitch of a muscle itself, it's not that one muscle is entirely fast twitch or another, or muscle is entirely slow twitch. It's kind of the ratio kind of between these. Okay. Because there will be times, when you need your muscles to act in a very fast, kind of, urgent way. But those same muscles might be used for something kind of slower and more sustained, and kind of, endurance is more value. Okay. And so, most muscles in your body have a certain balance. Okay. And interestingly enough, this ratio, or the exact ratio, kind of varies person to person as well. So that kind of, that can kind of explain why, that there are, I think this is especially interesting just because the Olympics kind of just happened. If you look at things like, track and field, or like swimming, where, yeah, these people have very athletic builds, but, it may not be immediately as apparent why, this really big dude is really good at throwing a rock or a stone, way further than this other really big dude, right? It's because, their ratio of fast and slow twitch muscle, in addition to the motor units inside them, all of these kind of have kind of pretty wild variations person to person. And so, I think that's kind of part of what kind of makes biomechanics so fascinating is all this variation. Okay. All right. Any questions on this? Okay. All right, let's move on. So that's kind of enough definitions for now. Let's talk about geometry a little bit. So let's talk about how the fibers are actually arranged in a muscle and how that affects its performance. Okay. So recall that, muscles can only really develop tension in the same direction as the muscle fibers. Okay. It's impossible for muscles to produce force that are perpendicular to the fibers, right? So whatever direction the fibers are running, that's the direction of the force. Okay. And so because of this, how the fibers are actually arranged in individual muscles and how they're arranged relative to the bones that they attach to, that plays a big influence in terms of, how much I kind of call it effective force that the muscles can actually generate. Really noisy in this building. And so if you look at kind of what I call a traditional muscle, or so kind of the first muscle that kind of everyone thinks of, they're often arranged in what's called a parallel configuration. Where the muscle is kind of just runs a single direction and all the fibers kind of follow that direction as well. So this would be kind of a parallel kind of a configuration, right? Where all the muscle fibers are kind of in that kind of the middle kind of bulbous section, right? And at the ends of this muscle, we have tendon. And so this would attach to a bone. Down here would attach to a bone, okay? And so when this muscle contracts, or when the fibers create tension, it just kind of naturally just shortens. Okay. You often kind of see this configuration in our limbs, and so in our arms and our legs, upper arm, lower arm, upper leg, and lower leg. All right. But not all muscles are arranged like that. So a lot of the muscles in our bodies have geometrical constraints, and so they have to kind of fit themselves into kind of a small space. And so they kind of have to arrange their fibers in kind of an unideal way. Okay. And so, it's kind of impossible to kind of draw every single configuration in your body because, there's lots of kind of, weird nooks and crannies that your muscles have to kind of jam themselves into. But kind of the general name that we kind of give for these configurations is called pennate. Okay? And so one kind of, general form is something that looks like this, right? So like, let's say that, your body has to generate force in a certain direction, but, the requirements of the amount of force that has to be generated, but also the space constraints may produce a geometry that looks like this. So let's say that you have kind of a single kind of trunk in the middle, and then your fibers kind of come out like this. And you have kind of a sheath that kind of surrounds this whole thing. Okay. So it kind of looks like a leaf if you think about it. right? So all those little tiny lines that I drew coming out, those are each individual muscle fibers, okay? So they're all gonna contract, but the direction of motion is not diagonal in this case. And so the direction of motion is actually up and down, okay? And so when all the muscle fibers contract, you know, what it's going to do is it's going to pull this kind of central stem here upwards. So this is a situation where, you know, the amount of movement or the magnitude of the movement is not very high, right? And so this stem is only going to move just a little bit up and a little bit down. But, you know, it's a situation that requires a lot of force. And so that's why there's a lot of muscle fibers that are attached to it, okay? And of course, you know, this is just a two-dimensional example. You know, there might be a three-dimensional, there's a lot of three-dimensional cases in your body where your muscle has to kind of wrap around kind of a weird area as well, okay? So this is a pennate configuration is quite common. And so kind of the classic kind of pinnated muscle in your body is your deltoid muscle. So the muscle that's in your shoulder, right? So if you look at your shoulder joint's kind of weird, and that the muscle has to kind of wrap around this kind of, you know, kind of socket like that. But you know, your deltoid muscle is kind of responsible for generating a lot of force as well. And so what you're going to see is that, you know, your deltoid is comprised of muscles that don't have fibers that run parallel to the motion that it creates. And in fact, you know, there's lots of very complex motion that has to happen in your shoulder as well. Right. So the deltoid is a very kind of common example. So although your deltoid isn't shaped quite like this, you know, your deltoid is kind of three-dimensional. Right? So as a consequence of having pinnated muscles, that not all the tension that your muscles develop will actually go towards the motion. Right? Right? And so, you know, we can just look at this geometrically as well, right? And so if I just take a single muscle fiber, right, like this, we know that the direction of motion is up and down, right? So we know the direction of motion in this case is kind of vertically up and down, but we also know that this muscle fiber can only generate tension, right? So it can only generate force that's parallel to that black line. Right? We should draw the opposite direction. Okay. So FM, or the muscle force, is only going to be in that direction. So if we just use trigonometry here, right? And so let's say we know this angle, and this angle kind of has an official definition. This is called the pennation angle. Okay. And so the component of force that goes in the direction of motion in this case is just going to be FM sine theta. And of course, that sine theta would basically, you know, if you think of trigonometry, that's going to be a number between 0 and 1, of course, depending on the angle that's there, right? So not 100% of that muscle force is going to go towards generating the motion. And of course, as the muscle moves, as the kind of the pinnated muscle kind of moves up and down, that pennation angle is going to change as well. Okay. And so there will be certain positions or certain, and probably you've experienced this as well, is that, when your body's in a certain position, it may be harder to kind of generate more force from that position. Part of that is because, you have pinnated muscles like this. All right. Any questions on this? Okay. There's another factor, geometrical factor as well, that's kind of separate from the pennation angle but also kind of goes towards this, this idea of effective force. Okay. And that is the attachment angle. And so attachment angle, what that refers to is the angle at which the muscle fibers attach to the corresponding bone. Okay. So let me give you an example here. Let me kind of draw, let's draw the arms. Okay. So let me go ahead and draw your upper arm bone like this. Here's your elbow joint. You're going to see me draw the elbow joint a lot in this class just because it's one of the easiest to draw. It's one of the few that you can kind of fully visualize in 2D as well. Okay. And that right there is the lower arm. Here's your wrist. And, we'll say the hand is like this. Okay. Okay. So there are a lot of muscles in your arm, but I'm only going to focus on one at the moment, which is the biceps brachii. Okay. So the biceps brachii kind of attaches, it runs kind of from the top of the upper arm and attaches kind of right past the elbow joint onto your lower arm. Okay. 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 So let's say that you have a situation where you're holding something in your hand, right? So let's say that, there's like a box or something. Okay. And so that's going to generate a force that's coming downwards, right? So that's just simply the weight of the box. Right. Now, holding this entire situation up is going to be, in this case, going to be just the biceps brachii. Okay. So biceps brachii, it's going to produce a force in this direction, Fm. Okay. And so let's say that you're holding this up, so you want to hold the entire arm static. Okay. And so what do we know about a static situation? It's in static equilibrium, and then all the sum of the forces have to equal 0. Okay. Not only that, but the sum of all the moments have to equal 0 as well, just so that there's no rigid body rotation. We'll go over this more probably next week. There's a lot of, we're going to review just some basic statics and basic mechanics. Okay. But just on first blush right here, right, you can see that because of the way that the biceps brachii is angled, right, not all aspects of that force are going to, contribute to counteracting the weight of the box. And so it needs to counteract the weight of the box, but it's not pointed vertically up. It's pointed up at an angle, right? And so if we look at this angle here, and so this angle right here, this is what we often call the attachment angle. To be a bit more specific, that attachment angle is the angle between the muscle fibers and the attaching bone. And so in this case, the attaching bone is your ulna, one of the bones in your lower arm. So even though I drew it on the vector right there, probably a more accurate spot would be kind of right here. Same thing though. And so, again, just kind of doing simple geometry, if we take the vertical component of that, it's going to be FM sine theta, right? Right. So again, because of the geometry of your muscles, we have a situation where not every component of the muscle is going to contribute to, contribute effective force. Okay. So that's going to be the theme for kind of the first half of the class is, looking at kind of the geometry of kind of how the muscle fibers are arranged in your body, looking at situations with kind of multiple muscles and kind of multiple kind of loading configurations and seeing, how much force that your muscles have to exert in order to kind of maintain this situation. Okay. And you'll be surprised that, geometry actually plays a really big, role. And so depending on that angle, that attachment angle, and sometimes the pronation angle, it's going to change your amount of muscle force pretty significant. All right, any questions on this so far? Okay. All right, so what happens to the other component of the muscle force, right? So this force here has kind of two components. So the other component is the FM cosine theta, right? So is that just wasted? Is that just kind of wasted work? Kind of. It's not exactly, helping you accomplish the task at hand, but it is kind of playing another role. Okay. So oftentimes you'll see me refer to this component of the muscle force as kind of the stabilizing component or the parallel component. So this actually plays a pretty important role as well. It may not contribute to kind of effectively producing a motion, but oftentimes this component of the force is gonna point directly towards the joint. Okay. And oftentimes it's a compressive force. And so this parallel component of the muscle force often is going to act to push kind of your bones closer together into the joint. Okay. And what this does is that this kind of plays a very important role of kind of stabilizing your joint. Okay. If you think about, if you have two, let's say you have two blocks of wood, right, and you want to prevent them from slipping past each other, probably the first thing you do is you just nail them together. But if you don't have a nail, right, what you would do is you would try to push them together as much as possible, right? And so by kind of exerting as much kind of contact force, you're increasing the amount of friction that's preventing them from sliding past each other. And your joints kind of work in a very similar way. Okay. So even though, we're going to see this kind of parallel component and it's going to seem like it's doing nothing, it kind of plays a very important role in stabilizing the joint. And oftentimes, when you're producing kind of very large kind of, motions, you're carrying a heavy load, we're going to talk about that a lot. Having that extra stability in the joint will help, prevent any kind of shearing or any kind of dislocation at that joint. Okay. All right. Any questions on that? Okay. There's a few more terms that I have here, but we only have 2 more minutes left in class, so let's go ahead and call it. So we'll finish up the last of the muscle biomechanics notes on Wednesday, and then we'll move on to joints from there. All right, so thank you guys for coming today. Hope you guys are staying cool. Hope you guys have a good rest of your day. If you're free at 6 o'clock, I'll be back here with Little Caesars Pizza, so stop by E101 if you have time. And I will see you guys around.
Hey, Professor, can you hear me?
Yes.
I had a quick question for you. I'm trying to look for these notes on Canvas, and I'm not seeing them, I don't think. I'm in the Files tab, but
There should be a tab called Lecture Notes, and so they're all there.
okay, got it. Yeah, these are dated 2022, but
Yeah,
They're fine.
notes haven't changed since 2022.
oh, okay, got it.
But I'm following the same order.
Got it. Okay, thank you.
Yeah.
Oh, yeah, it's just like all like 20 guys were